welcome to lecture 83. So, we have discussed last time about the trajectory transfer, and in that context we looked at that the minimum eccentricity transfer is the Human transfer, and also not always the Human transfer is the minimum energy transfer, but most of the time you will see that it is the minimum energy transfer. So, I will write the context in which the Human transfer happens to be the minimum energy transfer, and later on also I am going to work on that. When there is one more transfer, we call it the bileptic transfer. So, it is the combination of two Human transfer. So, using that also the transfer can be done, but whether the bileptic will be better or the Human transfer will be better, it depends on the intermediate orbit that is used for transferring the satellite from initial orbit to the final orbit. So, that will come over course of time. Let us start this Human transfer first, finish it, and then we will come over to that point. So, we can see from this place that the semi major axis of the transfer orbit, which is shown in here in green, on the actually the satellite is here in this place. This is the center of attraction, and from here let us say this is point A and this is point B. So, it is being fired here in this direction. The impulse delta V A is given here, and then again impulse delta V V is given here to achieve the. So, what is required that the statement is that at A in the inner orbit needs to be transferred to the outer orbit using Human transfer. So, Human transfer in general in the normal context, if we look at the earthbound cases. So, Human transfer will be the minimum is the transfer in which minimum delta V is required. The total delta V, the amount of the propellant you need to burn is the least one. So, satellite is at A, impulse delta V A is given here, and then again delta V B impulse is given at B. So, by giving impulse at A, we are sending it into the transfer orbit. So, here we can show this to be the transfer orbit. This is your transfer orbit. So, this working out is very easy, as we have done earlier. The specific energy is mu minus mu by 2 A equal to V A square by 2 minus mu by r. So, from here we see V A square will be 2 times mu by r minus mu by 2a equal to 2 mu by r minus mu by a. And mu either we can keep it outside. So, 2 by r minus 1 by a. So, V is available to us in this way. So, therefore, in the initial orbit the V will be given by mu by r I under root. Immediately you can see that for the circular orbit A equal to r, okay, and therefore, V becomes V I equal to, this is a square. So, we will put it in the form of a square root. So, V I equal to mu times 2 by r minus 1 by r under root. So, this gives you result mu by r under root. So, therefore, in the initial circular orbit we can put here c to indicate this is in the circular orbit mu by r I. Similarly, V f c is in the final orbit, the velocity will be given by mu by r f, and little bit of change we can do here to write it this way, r f by r I 1 by r I, and r f by r I we write as n. So, this gives you mu by n r I under root. So, this is nothing but V I c by under root n. Okay. So, we have written the velocity in the initial and the final circular orbits, there c stands for circular orbit. Okay. Thereafter, what will be the velocity in the elliptical orbit at A? So, we utilize this formula what we have derived here, V equal to mu times. So, V equal to mu times 2 by r minus 1 by a. So, V in the transfer orbit or in the elliptic orbit at A. So, for simplicity let us write this as V I in the initial orbit at point A, V just we write as V I E. In the E indicates elliptic orbit, E stands for elliptic / transfer orbit. And this can be simplified as 2 by r I minus a equal to r I plus r f divided by 2. So, 2 comes in the numerator, 2 mu by r I we can take it outside, and this results into 2 by 1 by 1 plus r f by r I. So, therefore, this gives you and this under root 2 mu by r I 1 minus 1 by 1 plus n. Two times mu by r I is okay. Mu by r I is V I c. So, that we will take it outside, and then we are left with 2 times 1 minus 1 by 1 plus n under root. This can be further simplified, plus 1 minus 1 divided by n plus 1. So, this is the velocity at point A. Velocity at point A in the transfer orbit. Similarly, VFE, which is the velocity in the transfer orbit at point B, and the at point B, this we can write as VFE, and using the same equation we can write here. A does not change for the transfer orbit, mu by 2 by R f minus 2 divided by So, we have got here in this format. Now, we divide both the numerator denominator by R I. So, this gets reduced in this format to my mu by R f by R I times, and R I we take common from the bracket. So, this gets reduced to R f by R I. Okay. Therefore, VFE, this gets reduced to mu by n times R I times 1 plus n under root, and mu by R I is nothing but our V I C. Okay. So, we are left with then 2 divided by n times n plus 1 under root. This is your VFE. So, now we know the velocity in the both the places. Okay. So, we can utilize these results, these two we have got here, which we have written here in this way, to find out how much the extra how much impulse is required at A and B. So, impulse required at A, this we write as delta V A. So, delta V A will be given by this V I E, which we have derived here. So, let us name this as, this we name as 1, 2, then 3, and this we name as 4. This one is the 4th. So, using 1 and 3, using equation 1 and 3, delta V A equal to, this is V I C, V I E, we will write this V I E minus V I C equal to V I C under root 2 n by n plus 1 under root minus V I C. We can take it outside common, and this is 2n plus divided by n plus 1 minus 1. So, this is the impulse required at the initial point. Using equations 2 and 4. V f c minus V f e, and V f c already we have seen this quantity is V I c divided by root n. That means, the inner orbit the velocity is higher because n is greater than 1. So, in the inner orbit velocity is higher, in the outer orbit, the outer circular orbit velocity is lesser. But energy wise the outer orbit is having more energy, this should also remember, E prime equal to minus mu by 2 a. So, here in this case if it is circular orbit we can just replace by 2 r. So, greater the value of r, the more positive this will proceed towards 0, as r tends to infinity E prime will be equal to 0. Otherwise, you can see that the larger the value of the r, the more energy the orbit will have as compared to a smaller orbit. But in the smaller orbit your orbital velocity is high. Minus V f e V I c times V I c times under root 2 divided by n times n plus 1. And the same thing we can also write this way, if we take V I c under root n as common. So, this will appear like this, means this is V f c times 1 minus 2 divided by n plus 1 under root. Now, this is the impulse required at the point B, and you can notice that this quantity is positive because n is greater than 1. So, delta V b is greater than 0 and also delta V a is greater than 0. Here also you can see this quantity is greater than 0. The way we have written. Okay. Sometimes the impulse is required opposite to the velocity vector. Okay. So, but always we can calculate, or even if it is coming in negative, you have to take its magnitude and work out. And therefore, delta V, the total impulse required is V I c can be taken as a common 2 n by n plus 1 under root minus 1 plus n by root n 2 divided by n times n plus 1 under root. Okay, so, this is the impulse required, total impulse required in transferring from inner to outer orbit. The same way it can also be done for the inner to the outer to the inner orbit. There is no difference in the working out mechanism. You have to write it in the same way. And this particular thing, whatever we have worked out, we could have gone by using this the energy approach. And through that route you will find that the same result will come, but it takes later on you have to solve the quadratic equation and then you will get the result only. So, the process is the same, but that is much longer. So, I will give you a write up about that, the other way of doing the same problem. Here I am not going to discuss this, because you do not get anything new in that particular way of working. Okay. Next, we will look into the bielliptic orbit. This is a bielliptic transfer orbit. So, it is a combination of two Hohmann transfer. So, one result I will write it here. If the final orbit is larger than, orbit is larger means it is a radius, is larger than both the initial and transfer orbits, then the Hohmann transfer always superior in terms of total change in velocity required. Okay, in that case you require the least impulse, and what is the region that I have already explained you, that if you are starting from this place in the inner orbit and then applying delta v impulse here in this point, so the always transfer in the total change in velocity not the impulse required. See, what I want to state here, that v plus delta v, this is the, if both are in the velocity v and delta v both are in the same direction. Okay, so, this will be your change velocity, and thereafter if you have both the velocities not along the same direction, this is your v and this is delta v, and this angle, let us say this angle is alpha, okay, and this is your v prime. Okay. So, v prime, as we have looked into, this will be given by v plus delta v, okay, and this will be equal to magnitude wise v prime, magnitude will be v square plus delta v square plus 2 v times delta v times cos alpha under root. Only when cos alpha equal to 1 you get this as v plus delta v square under root. If cos alpha equal to 1 means alpha equal to 0. In that case only you get the changed velocity to be the maximum. Okay. So, other way I can state that if the tangential impulse is required, so the change in velocity is maximum. And energy change, that depends on, already I have indicated, v plus delta v square minus this is delta E, change in the energy, because you are applying at the same point 1 by v square, this is the final energy, initial energy. So, v square cancels out, we get here 2 v times delta v and plus delta v square. So, you get the energy, this is the change in the energy this way, but if you have instead of v plus delta v, if we write this quantity, because this is then the magnitude, if we take the square on both sides, if we put a square here and this also be a square, okay. So, immediately you can see that the cos alpha factor will come here. Okay. So, the change in energy will not be the maximum. Here in this case you are getting the maximum possible change in energy. So, therefore, if the orbit final orbit is larger than both the initial and the transfer orbit, Hohmann transfer is always superior in terms of total change in velocity. Total change in velocity and also simultaneously I would like to state here that this part we have to remember that the transfer orbit is greater than the transfer orbit if the final orbit is larger than both the initial and the transfer orbit, then only. So, we will also have total impulse required will be minimum as we can see from this place, because of this, if the two vectors are inclined, v is here in this direction and delta v is here in this direction. So, we are not going to get proper change in the to achieve the same change in velocity. Here if these two vectors are inclined v and delta v. So, to achieve the same velocity you require more energy or the more value of delta v. What does this mean? That always we should apply, if v is the velocity. So, we should, if we apply delta v in the same direction, so we get the changed velocity v prime like this. But if it is v is here in this direction and delta v is in this direction. So, we are not going to, in spite of both being of the same magnitude, this v prime will be lesser in length. So, this is not efficient use of energy. So, here in this case you, if you are doing the Hohmann transfer. So, this is not only the minimum eccentricity transfer as we have proved earlier, but this also requires lowest amount of energy, provided the initial and the transfer orbit are both are smaller than the final orbit. If this condition is satisfied, this will be done. Otherwise, later on we will look in this bielliptic transfer orbit how the whole thing how the bielliptic transfer, in some cases it will be better than the Hohmann transfer, but for that certain conditions should be satisfied, and this we are going to explore in the next lecture. Thank you.